Hello viewers, I Nilofer Zargam, teaching in Center for Management Studies, Jamia Millia Islamia, welcomes you again to today's episode which discuss the concept of exponential and logarithmic functions and determines the break-even points as one of the functions related to business and economics through few illustrations. The script also helps us plotting some of the graphs of exponential and logarithmic functions. Let's take a broad overview of the concept of exponential and logarithmic functions first. It is a function in which independent variable appears as an exponent, that is power. For example, y equals to a to the power of x, y equals to 3 to the power of 2x plus 3, etc. are some examples of exponential functions. Y equals to a to the power of x, where a is a positive real number and a is not equal to 0, is the most popular exponential function. It is an increasing function, that is, as the value of x increases, the value of y increases when a is greater than 1. It is a decreasing function, that is, as the value of x increases, the value of y decreases when a is lesser than 1. In other words, a function with a constant base and a variable exponent is called as an exponential function. Y equals to a to the power of x, where x being a continuous variable and a is a constant, is an example of exponential function. The exponential function with positive base a, which is greater than 1, is the function given as y equals to f of x, which is equal to a to the power of x. For example, the graph of y equals to f of x, this is equal to 10 to the power of x. Following are some of the salient features of exponential functions. So the first one is domain of the exponential function is capital R, which is a set of all real numbers. Second, range of exponential function is a set of all positive real numbers. Third point, the point 0 and 1 is always on the graph of the exponential function. This is a restatement of the fact that a to the power of 0 is equal to 1 for any real number which is greater than 1. The fourth point says exponential function is ever increasing. That is, as we move from left to right, the graph rises above. The fifth point says for very large negative values of x, the exponential function is very close to 0. In other words, in the second quadrant, the graph approaches x-axis but it never meets it. Exponential function with a base 10 is called as common exponential function. It is observed that the sum of the series 1 plus 1 upon 1 factorial plus 1 upon 2 factorial plus 1 upon 3 factorial and so on is a number between 2 and 3, and it is denoted by e. Using this e as a base, we obtain an extremely important exponential function y, which is equal to e to the power of x. This is called natural exponential function. The base of an exponential function is usually chosen to be the natural base, e, whose value is 2.7182. There are certain advantages in using the natural base in place of any other constant base. The function y equals to e to the power x, where we have y equals to f of x, is smooth if and only if x is a continuous variable. Also, for all positive and negative values of x, the exponential function y equals to e to the power of x is positive. Graphically, the function y equals to e to the power of x lies always above the x-axis. In addition, the continuous function y equals to e to the power of x is monotonically increasing and single-valued and approaches plus infinity, that increases without bound as x increases, and the function decreases and becomes asymptotic to x-axis as x approaches minus infinity. Graphically, the curve is concave from the below, and the x-axis as its asymptote in minus infinity and rises to right while crossing y-axis at y equals to 1 and x equals to 0. The value of an exponential function is 0 when x is minus infinity. So we have a graph as an example here. The graph of a function y equals to e to the power of x rises above x-axis, meets the y-axis at point 0,1 and rises above from left to right. Figure 2 gives an illustration for this. If it would be interesting to know if the inverse of an exponential function exists and has a nice interpretation. This search has motivated the following definition. The logarithmic function is the inverse of an exponential function, and thus is defined by y equals to y to the log to the base a of x, where x is greater than 0 and a is not equal to 1. It is generally read as y is to the log to the base a of x. This can also be written as x equals to a to the power of y, which indicates that the inverse of an exponential function is a logarithmic function. In other words, the logarithmic of a positive number y to a positive base a other than unity is the exponent x of the power to which the base must be raised to the number. Thus, if a is greater than 0, a is not equal to 1, and a, x and y are so related that y is equal to a to the power of x. Let's make this equation 1. X is called the logarithmic of y with respect to the base a. This relation is expressed by x is to the log base a of y. Let's make this equation 2nd, where x is f of y. The two functions first and second express the same relationship between a, x and y in an exponential and logarithmic form. For example, let us find the unknown number y if log to the base 4 of y equals to 2. We can evaluate y equals to 4 to the power of 2, that is equal to 16, by writing it in the exponential form. Now again, for example, let's find the unknown base a if log to the base a of 9 equals to 1 by 2. Now by writing it in the exponential form, we get a to the power 1 by 2, which is equal to 9. This implies that a to the power 1 by 2, the whole raised to the power 2, equals to 9 to the power of 2. That implies that a is equal to 81. Since a negative number do not possess logarithmic, therefore the base of a logarithm can be any positive number except unity. Generally, there are two bases which are used extensively in mathematics and mathematical economics. These are the common bases, which is 10, and natural base, which is e, that is equal to 2.7182 approximately. That is, when a is 10, logarithmic function is of the form y equals to log to the base 10 of x and is called common logarithmic function. And when a is equal to e, logarithmic function is of the form y equals to log to the base e of x, and this is called as a natural logarithmic function. The natural base e is used mostly in quantitative economics. It may be noted that if no base is mentioned in the logarithmic function, it will be understood that the base is e. That is, y equals to log of x gives us y equals to log to the base e of x, or x equals to e to the power of y. If, however, there is a logarithm to the base other than 10 or e, the logarithm can be transformed to a logarithm with any base that we desire. For example, x equals to log to the base a of y equals to log to the base e of y divided by log to the base e of a. This is equal to log to the base 10 of y divided by log to the base 10 of a. It indicates that we can transform one logarithm with any base that we desire, with the numerator being the logarithmic of the given value and the denominator being the logarithmic of the base of the original logarithm. Some of the important observations about logarithmic functions to any base a which is greater than 1 are listed here. The first one is, we cannot make a meaningful definition of logarithmic of non-positive numbers, and hence the domain of log function is only R which are positive, that is positive real numbers. Second point says, the range of log function is a set of all real numbers. The third point says, the point 1 and 0 is always on the graph of the log function. Fourth, the log function is ever increasing. That is, as we move from left to right, the graph rises above. Fifth point, for x very near to 0, the value of log x can be made lesser than any given real number. In other words, in the fourth quadrant, the graph approaches y-axis but never meets it. Now let's see, logarithmic function possesses some certain properties which can be again listed down. The first one, log to the base a of x equals to y. So that implies that x is equal to a to the power of y. Second point, log to the base a of x plus log to the base a of y is log to the base a of xy. Third point, log to the base a of x minus log to the base a of y is nothing but it is equal to log to the base a of x divided by log to the base a of y. The fourth point, log to the base a of x to the power n equals to n into log to the base a of x. The fifth point, log to the base a of a is always equal to 1. Sixth point, log to the base a of 1 is equal to 0. Log to the base a of x is equal to log to the base b of x divided by log to the base b of a. This property is known as base changing formula. Now have a look on a graph of the logarithmic function given. Let's see example 1. If f of x equals to log of x, show that f of 3 plus f of 5 plus f of 6 equals to f of 90. The solution to this is f of x equals to log of x. So this implies that f of 3 plus f of 5 plus f of 6 will be equal to log of 3 plus log of 5 plus log of 6. And this is equal to log of 3 into 5 into 6, which is equal to log of 90 is equal to f of 90. So this implies that f of 3 plus f of 5 plus f of 6 equals to f of 90. Now let's see example number 2. Find the value of log to the base 3 of 81 under root 3. Solution to this comes as log to the base 3 of 81 under root 3 equals to log to the base 3 of 3 to the power 4 into 3 to the power 1 by 2. So that is equal to log to the base 3 of 3 to the power 4 plus 1 by 2. That is equal to log to the base 3 of 3 to the power 9 by 2. So that is equal to 9 by 2 into log to the base 3 of 3, that is equal to 9 by 2 into 1, which is equal to 9 by 2. Since we know that log to the base 3 of 3 is always equal to 1. So that is what we have used here. The break-even point is the level of production where the cost of production and the revenue from sales is equal. At this point, the company is neither making a profit nor loss. In other words, profit is equal to 0 at this point of production. That is, P of x, that is profit, is equal to 0. Or we can say that the total cost equals the total revenue at a break-even point. Now since profit function is defined as P of x, that is equal to R of x minus C of x, therefore P of x is equal to 0, it implies that R of x, that is revenue, equals to C of x, that is cost. Thus, when the revenue equals the cost, there is no profit or loss, and this value is called the break-even point. Symbolically, at the break-even point, we have C of x equals to R of x and P of x equals to 0. Graphically, break-even point is the point of intersection of the line corresponding to the cost function and the revenue function. Now let's take an example number 3 here. The daily cost of production C for x units of a manufactured product is given by C of x equals to rupees 4.5x plus rupees 11,000. The first part of the question says, if each unit is sold for rupees 5, determine the minimum number of units that should be produced and sold to ensure no loss. Second part of the question says, if the selling price is increased by 1 rupee per unit, what would be the break-even point? The third part of the question says, if 5,000 units are sold daily, what price per unit should be charged to guarantee no loss? Now let's see the solution to this. We are given that the cost of production as C of x equals to rupees 4.5x plus rupees 11,000. Now the first part of the solution is here. Since the sales price of 1 unit is rupees 5, revenue function will be R of x equals to 5x. Since we know for no loss, the condition is R of x should be equal to C of x. So that implies 5x equals to 4.5x plus 11,000. This implies 0.5x equals to 11,000. So that implies x equals to 11,000 divided by 0.5, which gives you 22,000. So there are 22,000 units to be produced. Now second part of the solution. When the selling price is rupees 6 per unit, R of x will be 6x. In this case, at the break-even point, we have R of x is equal to C of x. So that implies that 6x should be equal to 4.5x plus 11,000. So that implies that 1.5x equals to 11,000. So that gives us x equals to 11,000 divided by 1.5, which is equal to 7,333.33. So that is almost approximately equal to 7,333 units. Now let's see the third part of the solution. Let P be the selling price of 1 unit. Then the selling price of 5,000 unit will be 5,000 P. Now we have R of 5,000 equals to 5,000 P, and we have C of 5,000 equals to 4.5 into 5,000 plus 11,000. That is equal to 22,500 plus 11,000. This gives you a rupees of 33,500. So in order to guarantee no loss, we must have again the break-even point. Thus, R of 5,000 should be equal to C of 5,000. So that implies that 5,000 P should be equal to 33,500. So that gives us P equals to 33,500 divided by 5,000, which gives us 6.7. So the price per unit should be 6.70. Now let's come to example number 4. The fixed cost of X units of a product are rupees 95,000 and the variable cost per unit are rupees 30. If each unit is sold for rupees 150, what is the break-even point? Now the solution to this is, cost function is given as C of x, that is equal to 95,000 plus 30x. The revenue function is given as R of x equals to 150x. Now we know that at break-even point C of x is equal to R of x. So that implies that 95,000 plus 30x will be equal to 150x. This gives us 95,000 equals to 120x. So that means that x equals to 95,000 divided by 120, which gives us a figure of 791.66. So the approximately x is equal to 792. So at break-even point, we have x equals to 792. Now let's come to example number 5. A leather company starts a production of a new variety of ladies' bag. For the first year, the fixed cost for setting up the infrastructure comes to around rupees 1,60,000, and variable cost for the production of each of this bag is rupees 80. But the company gives production bonus to its employees. So the variable cost further increases by rupees 2.50 per bag. Now each bag is sold at rupees 350. Now what is the profit function, that is P of x, for x bags produced and sold in the first year? If 800 bags are produced and sold in the first year, what profit or loss would the company incur? What is the break-even point? So these are the questions to which we have to find the solution. So let's see the solution first. Let the number of bags produced and sold in the first year be x. Then the total cost is given by C of x is equal to variable cost plus fixed cost, we know that. So that is equal to 82 plus 50x plus 1,60,000. Since each bag here is sold for rupees 350, therefore the revenue R of x is given as R of x equals to 350x. Now the profit function P of x therefore is given by P of x equals to R of x minus C of x. So that is equal to 350x minus 82.50x minus 1,60,000. That is equal to 267.50x minus 1,60,000. So we have P of 800 now will be equal to 267.50 into 800 minus 1,60,000. So that gives us 2,14,000 minus 1,60,000. So that gives us a figure of rupees 54,000. This indicates that there has been a profit of rupees 54,000. Thus, in the first year of production of ladies' bag, there is a profit of rupees 54,000. Now we know that for break-even point, R of x is equal to C of x. Therefore, 350x will be equal to 82.50x plus 1,60,000. So that implies 267.50x equals to 1,60,000. So x is equal to 1,60,000 divided by 267.50, which is equal to 598.13. So x is approximately equal to 598. Hence, we see that a break-even point is attained when the production and sale of bags drops to 598 bags. Now, let's see example number 6. A cigarette manufacturing company introduces production bonus to the workers that increases the cost of cigarette. The daily cost of production of Y cigarettes, if given by C of Y, equals to rupees 3Y plus rupees 600. The first part of the question says, if each cigarette is sold for rupees 6, determine the minimum number that must be produced and sold to ensure no loss. Second part of the question, if the selling price increased by 50 paisa per cigarette, what would be the break-even point? Third part of the question says, if it is known that 1000 cigarettes can be sold daily, what price the company should charge per cigarette to guarantee no loss? Now let's see the solution to the first part. Cost function we know is given by C of Y, that is equal to 3Y plus 600. Revenue function is R of x, that is equal to 6Y. Now we know that at break-even point R of x equals to C of x. So that implies 6y equals to 3y plus 600. That implies 3y equals to 600, which implies that y equals to 600 divided by 3, that is equal to 200. So therefore, company must manufacture and sell 200 cigarettes to recover all cost. The second part of the solution. If the selling price is increased by 50 paisa per cigarette, then the revenue function will be here R of x, which is equal to 6.50y. Now at break-even point again we have R of x equals to C of x. So that implies 6.50y equals to 3y plus 600. That implies 3.50y equals to 600. That implies y equals to 600 divided by 3.50, which is equal to 171.4. So y is approximately equal to 171. Therefore, company must manufacture and sell 171 cigarettes to attain the break-even point. Now let's come to the third part of the solution. Let the price of one cigarette be rupees p. Therefore, the price of 1000 cigarettes will be 1000 p. Now the cost of 1000 cigarettes will be 3 into 1000 plus 600. So that is equal to 3000 plus 600, that is equal to 3600. Now to guarantee no loss, price of 1000 cigarettes should be equal to cost of 1000 cigarettes. That means 1000 p should be equal to 3600. That implies p equals to 3600 divided by 1000, which gives you 3.6. Therefore, the required price for a cigarette will be rupees 3.60. Now let's see example number 7. A company manufactures wall clocks for which P is equal to 2500 minus 4x. That represents the demand function, where P is the price per unit and x is the number of units produced. Fixed cost and the variable cost per clock here are rupees 40,000 and rupees 550 per clock respectively. Find the level of production at which the company expects to recover all its costs. So let's see the solution. Cost function here is given as C of x equals to 550x plus 40,000. Revenue function here is given as R of x equals to, we know that it is equal to price per unit into number of units. So revenue function R of x equals to 2500 minus 4x into x. So that is equal to 2500x minus 4x square. So the position at which all the costs are recovered is given by R of x equals to C of x. Now 2500x minus 4x square equals to 550x plus 40,000. So 4x square minus 1950x plus 40,000 equals to 0. So 2x square minus 975x plus 20,000 equals to 0. Here A is 2, B is minus 975 and C is 20,000 if we are considering this as a quadratic function. We know that the solution to a quadratic function is x is given as minus b plus minus under root b square minus 4ac, the whole thing divided by 2a. So that is how we are going to solve this question, and we'll take the values here, and the values will be minus into minus 975 plus minus under root minus 975 square minus 4 into 2 into 20,000. The whole thing is divided by 2 by 2. Now this is equal to 975 plus minus under root 950625 minus 160000. The whole thing is divided by 4. So that is equal to 975 plus minus under root 790625. The whole thing is again divided by 4. That gives us 975 plus minus 889.2. The whole thing divided by 4. So that implies x equals to 1864.2 divided by 4 and x equals to 85.8 divided by 4. So that implies x approximately equal to 466.05 and x equals to 21.45. So we have two values for x here. The company can recover all its costs either by producing and selling approximately 22 units or 466 units of a product. Let's consider f and g are the two functions of x. Then we have the following algebra that we can perform on these functions. The first one is f plus g of x is equal to f of x plus g of x. F minus g of x will be equal to f of x minus g of x, where f and g are two functions of x. Now C part says that fg of x is equal to f of x into g of x. Now f divided by g of x will be given as f of x divided by g of x. Now for this algebra, let's take an example. Given that the function f of x is equal to 6x plus 5 and g of x is a function given as x into 3x plus 4. Now we have to find the first one f plus g of x, and the second part f minus g of x, and the third part fg of x. Let's see the solution to the first part. F plus g of x is equal to f of x plus g of x, we know that. So that is equal to 6x plus 5 plus 3x square plus 4x. So that is equal to 3x square plus 10x plus 5. So that is the value of f plus g of x. Let's find the value for f minus g of x. We know that this is equal to f of x minus g of x. So that is, we can take the values as 6x plus 5 minus 3x square plus 4x. So that is equal to minus 3x square plus 2x plus 5. Let's see the last part. Fg of x is equal to f of x into g of x. So that is equal to 6x plus 5 into 3x square plus 4x. So that is equals to 6x into 3x square plus 4x into 5 into 3x square plus 4x. So that gives us 18x cube plus 24x square plus 15x square plus 20x, which is equal to 18x cube plus 39x square plus 20x. So that brings us to the end. Let's quickly summarize what we have learned today. We have learnt the concept of exponential and logarithmic functions and how to determine the break-even point as one of the functions related to business and economics. In addition to it, the script has also helped us plotting few exponential and logarithmic functions graph. So that is all for today. Hope you have understood the exponential and logarithmic functions in detail and how to determine break-even points at equilibrium situations while solving various business and economic problems. We'll see you again discussing about our next topics on sequences and series, where we'll learn about the arithmetic and geometric progressions. Till then, take care. Bye.